Everybody, thank you all for taking the time to come to my talk out of all the many you could have chosen. I'm quite flattered there's a lot of people here. People at the back, there are a few seats sort of in this area. A trick from the previous talk by Darren Hubert, if there's anyone got a spare seat next to you, can you put your hand up and people at the back who may want to sit can come in and do that? Cool. Okay, so my name's Orion Edwards and I don't work for Microsoft, although I've got this nice Microsoft shirt here. I work for Gallagher in Hamilton, makers of agricultural equipment and electric fences, but we also make a bunch of other stuff, including some cool, a really nice security system, and we're really good. I'm really happy working there. They're a really great place. So this talk is about programming. I think there's a lot of really awesome things going on in tech space these days. Clouds and BIs and SQLs and Azures and things like that. But it's easy to lose sight of the fact that to make all that stuff work, people have to sit down and write some code. And that's what I want to focus on. So this talk in particular, I'd like to talk to you about a few things I've learned along the way. Now, a story that I have, a few years ago, there was a question on, I think it was Stack Overflow, that said, what is the single most effective thing that you've done to become a better C# programmer? And my answer, which I put in Stack Overflow, I got a few upvotes for this, was to learn Ruby. So some people might think, well, hang on, the best thing you've done to become a better C# programmer is to learn Ruby? And the answer for that was yes. At the time, this was some years ago, C# didn't really have much in the way of functional programming and lambdas, whereas Ruby, on the other hand, has got lambdas coming out its ears. And for me, learning Ruby really kind of exposed me to that different kind of mindset. And then I sort of applied that back to C#, and that was a real sort of level up moment for me. So, which brings me to the title of this talk. So I'll read this out, because we all will. This is a quote from Steve Jobs. Picasso had a saying, he said, "Good artists copy, great artists steal." Now, he got a bit of flack for this because it was with an interview in about 1994. And that was about the time when Apple was suing the pants off Microsoft for ripping off the Macintosh UI in Windows. And here's Steve Jobs, the CEO of Apple, saying, we should steal things. Second damning thing about that was he was actually wrong. Picasso never actually said any such thing. But if we take our sort of, that makes for a great soundbite, and which is why I've chosen it for the topic of this talk. But if we look at the full quote, sort of in context, the bit that comes before it in the video, Steve Jobs says, talking about design and things like that, it comes down to trying to expose yourself to the best things that humans have done, and then try to bring those things into what you're doing. Now, Picasso didn't say that, but a bunch of other people did. And it traces back to the famous poet T.S. Eliot from hundreds of years ago, or whenever it was. And they all focus on this idea of stealing things versus copying. And the distinction they draw is kind of like what Steve Jobs is trying to get at here, which is, let's look at what's out there, figure out what is it that makes those things good, and then try and bring those things that make it good back into what we're doing, but bring it in a way that makes a cohesive whole, rather than just carbon copy, sort of let's just stick this thing in here without any concern of whether or not it actually fits with what we're doing. So just a few agenda here. If you'd like to contact me or ask questions or anything like that, the best way to do that is just on Twitter at Borland. This talk has got two sort of parts. So the first few examples are smaller things. They will not take as long. And the second two, the Grand Central Dispatch and the channels, they're sort of bigger things that take a bit longer to get into, but potentially more valuable. So, now, one piece of advice that they give you for being a speaker is you should put pictures in your presentation. You shouldn't put lots of words, you should put pictures. People remember pictures. I'm no good at pictures, I'm going to give you code. Here's some pictures of some code. So, start with Ruby. Anybody here used Ruby? A few people, not very many. Okay, that's good. I was thinking that perhaps everybody would just be like, oh, I know all this stuff already. So, in Ruby, if you'd like to open a file, this is the recommended way to do it. You call the file.open method, and you pass it file names and stuff. And you have this do end thing. So that in Ruby is a lambda. What it does is it opens the file, passes the file handle to the lambda. You then do with it as you will. And at the end of that lambda, it closes the file and ensures that you don't forget to do that. Now, okay, so before we get going, most of the examples target this in C#. The subtitle of this talk could have been doing lots of cool things in C# that you didn't think you could do. People here familiar with C#? Cool, excellent. So you might think, well, I don't need to do that in C#. I've got using blocks, and that is correct. It might be more interesting, though, to do it in something like a database transaction. So it's similar to a using block in that it forces you to close the transaction. But the advantage of this approach is that you can't forget. You can't just have some junior programmer come along in a year and start a database transaction and forget to put a using block in. The compiler simply will not let that happen. So that's one thing that you can use this pattern for. But it's not just good for database transactions. So how's my font size? Everyone can read that? Cool. So this is a small web app. And in here, I've just an MVC basic page. I've got this HTML data table method, and I'm passing it a lambda. And in that lambda, it does a bunch of stuff and then applies the result at the end. So this is building a table. If I run this app, then you'll see there's my table. I've got 3 people in it. And the trick here is that the lambda here is effectively building up some environment, and then the environment is not applied until the end. Now this particular technique is used in Ruby on Rails a lot. That's how they configure their app. And we can do stuff like make another column, stick the age in there, and as you can see, it just redoes the table. Now there are many, many ways to make tables in MVC. We use a technique like this back in a project back at work. It's really handy just for really, really quick, simple spitting stuff out. So when is this a good idea to use this pattern? Well, if you've got a resource that you really don't want to leak, like that lock or like a lock or a transaction, if you've got some kind of custom lock. It's also good for that whole build up, then apply. Configuration can be good. Templates, like my HTML example. It's also really strong with batching. If you've got a bunch of stuff like you might want to create a whole lot of network calls to a service. What you can do is you can have a lambda, which is a batch, do all the calls in there, and it can scoop them up and apply them at the end. Maybe not for things that don't need restricted lifetime. So in Ruby, you've got that file open, it forces you to close it. You might not necessarily want to close the file. For those kinds of situations, just use iDisposable. Now, the idea here is not from Ruby. Ruby did not invent lambdas. The idea goes all the way back to Lisp in 1958. And the idea here is code is data. So really, code is not just for executing. It's not a straight line. CPU doesn't just go ABC. You can take some code, stick it in an array, run it later, put some scope around it. Hopefully I can get people thinking a little bit more about what you can do with code rather than just straight line execution. Now, next thing is naming. This is some C# code. We're drawing a line on a canvas, and we've got some numbers there. So you can probably guess the 10s and the 30s are something to do with x and y's and widths and heights, maybe. That true? Who knows? So if this method were in Objective-C, it would look like this. So you've got canvas line from x, from y to x to y. So the parameters are named, and it's forcing you to say what this thing is. So you might think, well, OK, name parameters, that's cool. In Objective-C, they're not name parameters. The method name is this. Objective-C does the interesting thing of putting the parameters in the middle of the method name, not at the end. But it achieves the same result. And so how can you apply this in C#? Well, C# has had name parameters since 2010, I think. But I haven't seen them so often used. Now, what I'd like to encourage you to do is try and take that idea from Objective-C of using name parameters and applying them as a sort of a phrase, rather than just, here's my method name and I've got some parameters at the end. Try and consider the parameters as part of what the method is all about. Now, I did a test run of this talk back at work to the devs there, and it was quite interesting, the feedback I got about this particular one. A lot of the senior devs were like, oh yeah, that naming thing, whatever, just it's not really that important. But the less senior devs, quite a lot of them actually said, well, no, that's, particularly the ones that have worked with Objective-C, said, that's the best thing about Objective-C, it's really good. I can come into some code that I'm not immediately familiar with, and I have a much better idea of what it's doing. I thought that was quite interesting. The senior devs and the tech leads and so on don't tend to have that problem because they've been there for years and they know how everything works. But certainly for introducing new people to a project, this kind of style really can help. So, the next example is from Swift. Swift is relatively new, if you're not familiar with it. It's a language that Apple introduced a couple of years ago. It's their replacement for Objective-C, because Objective-C is kind of old and clunky. And I really like Swift. Swift kind of embodies what I'm trying to get at for this talk, is it takes a lot of good ideas from a lot of programming languages, and it kind of merges them together into this different language. So in here, I've got a function called readFile, takes a parameter called path, and it's a string. And the return value for that method is a string question mark. So string question mark in Swift means a string that might be null. If any of you have ever seen anything to do with F# or Haskell or any of those kinds of things, they have this idea that something that types just can't be null by default. And you have to sort of say deliberately, this one can be null or not, as opposed to something like C#, where any reference type is allowed to be null at any time. So why might you want to do that? Well, anyone who's worked in a large system has probably seen a lot of crashes with null reference exceptions. And they indicate a problem in your code, but the worst thing about them is not that there's a bug, but that you don't know what the problem is. You've got a null reference exception. The problem is probably not the null reference exception. The problem is probably 2 or 3 lines further down the track. Someone else did something wrong, which later on caused the null reference exception. You'd like to catch the problems when they occur, not sort of indirectly later on. Interestingly, Tony Hoare, the inventor of Algol, is quoted as saying, and sort of it seems to be that he's the inventor of the null pointer, has been quoted to say that's the worst mistake he's ever made, and people have mentioned null pointers as the worst mistake in computer science. So it's really nice if your compiler can help you prevent them. So in Swift, our ingoing string path, it's not allowed to be null. The compiler will not let you do that. Outgoing string might be null. So how do we deal with that? Now Swift has this if-let statement, which takes a thing that might be null and unwraps it. That's what they call it, unwrapping. And so what it does is if it isn't null, they assign it to this new local variable contents. Then we proceed and we're safe, and we guarantee that at that point contents is not null and we can do stuff with it. There's also an else condition where if it is null, we run that. So you think, okay, how can I do this in C#? Well, you can't change the compiler. Eric Lippert and a few other people on the C# team have said they would have liked to not have null references. But there's too much water under that particular bridge. I think they said I'm paraphrasing here, but I think the original reasoning for null references was compatibility with Java. Thanks, guys. What you can do, though, is you can create a wrapper object. So if any of you are familiar with, can't remember exactly which version of C# this came in, there's a nullable type. You can have int question mark, double question mark, that kind of thing, which normally you can't have null ints. That lets you have null ints. The point of this is to apply that same kind of really basic wrapper to reference types. Incidentally, all the code for all the demos and more code for more things that didn't make it in is up on GitHub at that URL. It's all under a do whatever you'd like with it license. You're more than welcome to go and have a look if you so desire. So anyway, I'm going to return this wrapper structure. Now you might ask, a string can already be null. I'm returning another thing that says it might be null. What am I achieving here? Well, I'd like to show you. So in here, I've got my app with a main function, read file, kind of similar to the Swift one. If we look at the function body, it's a basic demo function. It reads all the text in a file and returns it. But if there's no such file, or if it gets an exception like permission denied or whatever, it just returns null. So compiler's quite happy. Let's run this code, run this program. And boom, null reference exception, because that file did not exist on the disk. So what we can do here is I'm going to change this method signature to return optional string. Now you might see that the method itself is quite happy. That's because the optional class, I'll just jump and show you it. It's quite simple. It's got half a dozen methods. The only thing relatively complex is equality, because equality is always complex. Otherwise, it just returns the underlying value. But it does have an implicit conversion operator, so you can just return a string or return null, and the compiler will implicitly convert it into one of these. It's nice and easy. Now, the good thing we do see is over here, we're now getting a compile error saying we can't do .length because this optional thing doesn't have a .length. You need to consider that it might be null. So we can do that. Just like the nullable one, we can go if data has value, and then data.value. That's cool. What I've also done, though, is I've put some helper methods on this thing to try and mimic that sort of concise syntax that Swift gives you. So what we can do is we can go data.unwrap. So unwrap, you give it a lambda, and it will only run that lambda if the thing is not null. So we now have a safe program. It will not crash. It will not compile either, because I need one more bracket. And it didn't do anything. The file was null. If we point it to a file that actually does exist, then you can see it worked. Now unwrap has another, you can pass it a second lambda for the else condition and so on and so forth. Like that. Where should you use this? Well, for my money, if you have any functions at all that ever sometimes return null, you should use this. As an exercise, I put this kind of thing into a couple of projects at my work a couple months ago, and all I did was search for, just find and replace, just global search for return null. And any of those functions that had return null in them, all I did was change the return type to optional, just like you saw there. Now this of course causes compiler errors because the guys that call them aren't expecting it. So you go through and fix them and pass the optionals up the chain and so on and so forth. And at the end of this process, now I did this to a couple of medium-sized projects, maybe 50, 60 C# files each. And just that process alone, I found about 8 actual legitimate bugs. I thought that was pretty good bang for the buck for a 10-minute exercise. Maybe not for input parameters. You might be tempted to think, well, okay, that's cool. Let's use it as a decorator to say, I'm allowed to accept null here. You could certainly do that, but the value is not so much. The value is really about communication. Programs are meant to be, this is a quote from somebody, can't remember exactly who off the top of my head, but programs are not meant for people to read and only incidentally for computers to execute. So the key thing here is communicating. If I'm returning a value from a function, I need to communicate that to anybody in the future who might need to deal with that value. If I'm accepting a value from anybody, I don't need to communicate that any further than the insides of my little function. So naming conventions are probably a better option there. The unwrapped lambdas, those are nice. I quite like them, but they work best for small things. If you've got larger, more complex code, you might be better off with just if has value. And the reason for that is lambdas make debugging difficult. It's hard to sort of step next and that kind of thing when you've got too many lambdas. The other interesting thing about this is that this pattern generalizes. You can't you can do other things other than just optional string. You can do atomic bool or atomic string, and you can put some locking and stuff like that in there. You can have tainted. Tainted is a thing that Perl has. Ruby also has it. Tainted is meant to signify that this particular piece of data has come from some untrusted source, like an evil web form, and it's probably full of SQL injection. And you need to deal with it appropriately, as opposed to a regular string which you might trust. Incidentally, ASP.NET MVC kind of does this, but they use a different approach. They have a iHTML string, which is a safe string, but it's the same kind of approach. It's a wrapper over something else to give it some additional meaning. The next thing we're going to move into, it tails into the previous one nicely. You'll see why soon. This is a snippet of C++ code. I've got a double, and I've also, same as in C#, just a 64-bit floating point number. But I've also got a structure called meters, which has got a double inside it. So you might think, well, what's the difference there? Well, a double is just a number. It can be anything. It confers no meaning. It might have meters in there. It might have miles. It might have Celsius degrees or something like that. Whereas this wrapper structure of meters, it's saying this thing that I have inside me is a unit of meters. Now, the interesting thing is that a double is 8 bytes. That's how big it is. This wrapper structure, which contains one, is also the same amount of memory. It does not cost you any memory. So, hey, that's cool. Now, if we actually do some operations with this, we've got our example 1. We're just doing 100 plus 100. Or we've got our second example using these wrapper structures, where we're adding the two together and just assumed that our meters has a overloaded plus operator, which allows you to do that. Now, in C++, these turn out to be equivalent to each other. The overloaded operator will get inlined by the compiler and optimized effectively to the exact same thing. Now, the principle behind this is called zero-cost abstraction. This is a main design goal for the people designing C++. They want to let you use lots of abstractions and high-level features, but not have to pay the runtime overhead. Now, that's a different goal to other languages like, for example, Ruby, which gives you lots of expressiveness and power, but you pay for it. It's much slower, and it uses much more memory. So that's cool. It's good for C++. Maybe you want to use C++, maybe you don't. You probably don't, because this particular example here, I've got 7 or so lines of code. When I did this trial run, our programmers at work pointed out about 5 errors in about 7 lines of code. That's pretty bad, especially given that I did a talk about C++ template metaprogramming at CodeMania last year. I kind of think I hopefully know C++. The good news is you don't have to use C++ for this. This particular feature turns out to be true for structs in C# as well. So in my demo here, I've got this wrapper struct. It's got a double value. You can assign it. It's got the implicit operator to sort of convert. And it's got a divide operator, so we can do safe division, and it returns the meters per second. So it allows you to do maths, but in a safe, constrained form. You can't do meters divided by kilograms, because that doesn't make any sense. And I've also got some other wrapper structures for seconds and other kinds of units. And I've also got down here some methods which just do maths. It's the same kind of maths. And I'm just going to run them in a benchmark, and we're going to see what's going to happen. So we make an array of 1 million doubles. Uses that much memory. We make an array of 1 million of these wrapper structures. It uses the same amount of memory. So we're getting that for free, just like C++. Now, our direct maths takes about 200 milliseconds, and our wrapper maths takes a lot longer. So hang on, you're telling us we get it for free, but we don't? Not in debug mode. In release mode, however, it turns out the wrapper structure is actually faster. Now, it shouldn't be. It should be about the same. I kind of think this is down to margin of error, but every time I run this, it's always faster. So there you go. Now, you may have noticed also that such a wrapper structure, that optional is exactly one of these things. So I've just shown that, generally speaking, that optional, if you're putting it in your code, does not cost you in either memory or performance. So when should you use them? Well, you already do. System.datetime, time span. It's exactly what these things are. They're just wrapper structures over 64-bit numbers. Where they are really useful is if you've got multiple data types being combined together, doing maths and things, distance and speed. Or if you've got a unit of measure that's important in there. So the sort of next thing for this is a wrapper structure with two values doesn't consume any additional memory than just those two values by themselves. So you can have a unit plus a tag like a New Zealand dollars versus US dollars or so on and so forth. A few years ago there was an incident of a Mars rover that they burned $100 million or so because it went all the way to Mars and then did the wrong thing because one of the teams wrote in miles and the other team wrote in kilometers. Now, I'm not saying that this technique would have saved them there because they're probably using some other interface, but it's worth considering. Certainly, I don't work in banking or finance or something like TradeMe, but if I did, you'd bet I would want to know, whenever I'm passing values around, what is the unit of this? Is it New Zealand dollars, so on and so forth? Maybe not for standalone parameters. So you could enforce that your timeouts are always in time span, your delays are always in seconds, wrapper structures, and so on and so forth. You don't always need to do that. Naming conventions are often sufficient, and it comes back to that same reason of returning the optional. If you're accepting data in, you don't need to be quite so constrained as if you're returning it out. It comes down to that communication. Now, if you just write int delay with timeout, and you don't put milliseconds in there, then I will come to your work and I will be very angry at you. So you need to at least put something in there to indicate the unit. Now, the C# and C++ and these kinds of language, they didn't invent this stuff. Haskell probably invented some of it, but even then, probably not. But anyway, the lesson here comes down to something from Haskell. And it's been said that if you can actually get a Haskell program to compile, it probably is free of bugs. And I don't like Haskell for that reason. It's too hard to get anything to work. But it's a good lesson to apply. The compiler, via use of things like wrapper structures and tags and things, so on and so forth, can help you stop writing bugs. And you should try and consider that and use that. So, moving on to the second part of the talk. I've got two things, and they relate to concurrency. Why concurrency? Well, as we all know, even cheap phones these days have got quad-core processors in them. You need to consider how to use multiple cores. Also because I think that there's a lot of interesting things going on in that space as well. So, Grand Central Dispatch is from Apple. Anybody familiar with iOS or Mac programming? All four of you, cool. Now, it's quite a different universe over in the iOS side, as opposed to Windows and C# and so on and so forth. Grand Central Dispatch is Apple's concurrency solution. And they have, rather than using threads and tasks and things like that, they have what they call queues. Now, a queue in Grand Central Dispatch parlance is a lightweight thread. So it behaves like a thread, and you get it to run stuff. But they don't actually consume operating system threads, so they consume less resources and you can have more of them. You get them to do stuff by effectively firing them a Lambda function. You say, run this Lambda, and off it goes. And the system itself manages these things. So it has three kinds of queues. The first kind of queue is a main queue, otherwise known as a UI thread. So this code is in Swift. It looks similar in Objective-C. The framework's the same. There's just more brackets and stuff. It's harder to read. But anyway, what I'm doing here is I'm calling dispatch async, and you feed it a Lambda function. That's the brackets at the end. And you call dispatch get main queue, and what it does is it takes that Lambda and fires it at the main queue, which is your UI thread in your UI application, and it will run that Lambda. C# equivalent in WPF is something like this. WinForms, it's control.beginInvoke. WinRT, it's, I can't remember exactly, but it's similar to this. Run a Lambda on the UI thread, cool. It has concurrent queues, otherwise known as parallel queues. So what these are for is these are managed by the system, they're built in, and you feed it, you get a concurrent queue. So I'm saying get global queue with default priority. So it gets me that default queue, and I fire a Lambda. Now what it will do if I fired 1,000 Lambdas, it'll run them all in parallel, using as many CPU cores as you can have. Ho-hum, task.run, or thread pool, queue user work item. There's a ton of ways to do this in Windows. Now, the thing that we don't have is this concept of a thing called a serial queue. A serial queue works like this. You create one, and you get it to run a Lambda, just like the other two. You can either do asynchronous, so you say, run this Lambda, do it in the background, I'll carry on. Or you say, run it synchronously, so block and wait. Similar to the dispatcher begin invoke versus dispatcher just regular invoke in C#. There is no built-in equivalent in C# for this kind of thing. So just to go over what's actually happening here. In my system, I've got 2 worker threads. Maybe my computer's got 2 cores, something like that. And I've got 3 of these serial queues. Now, I could have 3,000. It doesn't really matter. The point is that you don't have to have the same number as you have of CPU cores or worker threads. And what happens? So Q1's got some work to do. It will feed the first part of that work into an available worker thread. What it won't do is feed the remaining work. If this was just a whole bunch of task.runs, it would run them all in parallel, all at the same time, as much as it possibly can. And then you would have race conditions and deadlocks and all that good stuff. Now, the serial queue will only run one thing at a time. That's why it's called serial, and it will run them in order, just like a thread. So on and so forth. If more work arrives for another queue, then that can then run. So you can see here you could have 1,000 queues, and they're all running things in the correct order, and only one at a time. It's all nice and safe. And you're kind of multiplexing that down into a smaller number of operating system threads. The other interesting thing is that the queue jobs don't have to go on the same operating system thread. They can run on any thread at all, provided they meet that requirement of not running in parallel and running in the correct order. That leads to an interesting property when it comes to synchronous dispatch. So what that means is that if the queue is idle, it just locks. It doesn't do any thread jumping. Now, parallel to this is in something like C# with a UI thread. You may have your background thread and you want to say, run this code on the UI thread to update the UI and wait for it to finish. In order for that to happen, you have to post something to the UI thread, wait for it to stop, do the work, and then wait for it to finish. With serial queues, it doesn't have any of that. It just says, I'm free, do a lock, done. It's no more costly than a lock. If the queue is busy, then it does have to do that whole wait for him to stop, spin around, done. But the interesting property for this is that it means that you can think of a serial queue as a thread, more or less, a lightweight thread. You can also think of it as a lock. Imagine if the C# lock had a .run when finished. It's like that. Now, for me, I thought that was really kind of cool. So, how are we going to do this in C#? So, you might imagine there's a class called serial queue, and you have dispatch async and dispatch sync. And what it would do is run those things concurrently on some kind of thread pool, like the .NET built-in thread pool. Now, that doesn't exist in C#. As a proof of concept, I thought, can I write this thing? Because I can't very well talk to people at Ignite about how awesome this thing is if it doesn't work. As it turns out, it does. And unlike the other code in my other demos, which is all experimental and, hey, this is a cool idea that you might want to apply, I thought, actually, no, I want to use this for real at my job. I'm going to make it a real thing. So it's a real project up at GitHub, a separate project. MIT licensed. It's undergone a reasonable amount of testing. We're using it for real in anger at my job, flushed out a lot of the bugs. And I'm going to show you how it works, the API for it. So I've got an example app here. And in my example app, I've got some code which measures memory, and basically it goes and does a bunch of busy work. So it's parsing some XML, that kind of thing. It's meant to replicate what you might have in a back-end processing app. And I've gone and got a class called ThreadQ, which has the same API as a serial queue, dispatch sync, dispatch async. It's a pretty simple API, but it just uses a thread. So fire that up, 200 queues. So this is 200 threads here, operating system threads. You can see we use 74K of memory, but we use 260 megs of virtual memory. So that's an interesting stat there. And it takes about 52 milliseconds to run all that stuff. If we crank that up to, say, 2,000, we use 700K of memory, but we use 2.6 gig of virtual. So the reason that's happening is because when you create threads, each thread needs about a meg of reserved space for its call stack. And it needs to basically ask the operating system to guarantee that that can be there. Now, why this matters is in a 32-bit process, you only get 4 gig. Then you run out of memory and you crash. And in reality, that limit ends up being realistically lower than that, because your app is not just running demo stuff like we're doing here. I've found with our real large .NET sort of apps that we've got back at work, once .NET Framework hits about 1.5 gig on that virtual, it tends to run out of memory and die. So you really need to be conservative with that kind of thing. Now, you could switch to 64-bit, problem goes away. You can have terabytes of virtual, but you may not be able to do that. You may have existing code which only works in 32-bit. You may have native interop. The performance of the 64-bit JIT compiler, even the new one, is still not as good, so on and so forth. Anyway, it takes about 900 milliseconds to run that. Just for argument's sake, we'll crank that up to 4,000 threads. Boom, out of memory. You can't even create 4,000 threads, let alone run them. We go back to that 2,000. Remember how much memory it took, and it took about a second to run. I'll switch over to serial queue. Now we use 300K of memory, under half, and we use 20K of virtual. So we're using less virtual than we are actual memory. So the reason that's happening is because .NET garbage collected language, it's always allocating more virtual memory from the OS than you need. It'll only ask for more when it needs to. So we're not even hitting that boundary. And it takes 200 milliseconds. So that concept of rather than having all the threads running and the operating system switching them, we multiplex them down into a smaller number of operating system threads. It means there's far less switching done by the OS, which is far more efficient. It takes about a quarter of the time to do my busy work. Your benefits will be more or less depending on the workload. And for argument's sake, let's crank this up to 10,000. Now we couldn't create 4,000 threads at all. We can quite happily create 10,000 queues, 1.5 megs of RAM, and it takes a second. So you can see they're much, much more efficient, while still preserving that same API and that same safety of running things sequentially and not having to worry about locking and so on and so forth. So where should you use these things? Now, the Apple guidance, when they introduced these things a few years ago, was basically you should just use them always. Don't use threads. Just don't even write code that makes a new thread. Just use these instead. Now, there's always like really quirky edge cases, but by and large, these are fine. Does that apply to C#? I would say potentially yes. I would not really go and write any more C# code that made a new thread anymore now that we have this, unless it was, again, one of these really crazy edge cases. What they're also really good for is if you've got an actual queue. So an example from my work is we've got a server that talks to a number of network devices. This might apply to IoT sort of situations as well. And you need to talk to these network devices in order. You need to queue the messages. You don't want to just send 20,000 packets in parallel to a Raspberry Pi. The serial queue is really nice there because you can just put all the stuff in the queue and it will run it all in order. It behaves like a thread, so you can get it to do things like pause and sleep and so on. It works really well there. It's also nice if you've got existing code. It might have been around for ages where you've got lots of threads and maybe you're using too many threads and running out of virtual memory and finding it hard to use the debugger because you look in the parallel stacks window and there's 10,000 threads. It's really easy to just drop this in because the I guess, conceptual model is very similar. But where this gets really interesting is that it opens up a new, I guess, design space. So going back to those examples of, you've got a UI thread. Now, most UI frameworks have a UI thread. And all the stuff that has to be related to the UI has to be on the UI thread. WinForms has it, Win32 way back has it, WPF has it, the new WinRT, Windows 10 Universal Apps, they all have this model. So does Apple, so does everybody else. On the other hand, you've got full-on multi-threaded, all the code runs on all the threads, and you have to be very careful about locking and stuff like that. Because these serial queues are so much more lightweight and so much more efficient than something like a thread, you now have this new middle space where you could say rather than every single UI component running on the UI thread, you could have each UI component potentially have its own queue. And you'd still have that same safe model, but not be tied to one physical thread. So you'd be able to use more cores. Now, where are these not so good? Basically, if you don't need those features of running things sequentially, if you've just got a bunch of number crunching to do, and it doesn't share any data, it's all just maths, just use a bunch of tasks. That's what they're for. Also, basic locking. Now, in the Apple world, people actually will use serial queues instead of locks because the locking APIs are not so nice. C# has got a really nice locking API, just use that. Now, the final major topic is from Go. Go has a few interesting properties. It's meant to be a low-level sort of systems programming language. It's by Google, and its sweet spot is building services and things. So people have used it. I've seen quite a few now online and blogs and so on. People using Go for things like push notification services, sending backends of emails and things like that. And the reason they do that is because it has an interesting concurrency model. So Go takes that kind of like a serial queue, where you've got these virtual threads, but let's take that further and let's just say, what if each function could run in its own virtual thread? And so this code here, I've highlighted the interesting bits in red. That Go keyword says, take that function and run it in parallel. So now you've got all of these functions running in parallel. How do they communicate data around the place? Go has this thing called channels, which let you send and receive data in between all of these parallel functions. Now, the send and receive is that funny backwards arrow thing. So how does this actually execute? Now, they call them Go routines because trendy name. Effectively, it's just running a function in parallel. Our main function starts off. It makes a new channel. So a channel is like a conduit for values. So they're making a channel called result, and this channel lets you pass integers. You can pass anything. The next thing we do is we call that Go multiply, which runs that multiply method in parallel. So the multiply method runs, does its work. The main routine runs, printfs, print lines. Then, when we hit that funny backwards arrow in the multiply method, we want to send the value to the channel. Now, the interesting property of sends and receives on channels is that they block, which we'll get to later. So that method can't proceed until someone else on the other end is ready to receive that result. Meanwhile, our main routine is doing some sleeping. Eventually, it reads that result unblocks the other end, and carries on. So Go routines and channels. Well, Go routines running a method in parallel, task.run. We're coming back to this a lot. Task.run is pretty cool. Channels, on the other hand, are quite interesting. They let you, the send and receive methods are a nice way to pass data in between all of these things that you've got going on in parallel. What they do is they block the method, and the reason they do that is for safety. If you've got a method that's reading lots of values, it needs to pause while it's not reading values, otherwise it will read them all concurrently, and then you'll need to introduce locks, and you'll have race conditions and that kind of stuff. So blocking the reader is for safety. Blocking the writer is also interesting because it means that things keep pace with each other. You could just say send, 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 and they all just sit in some buffer somewhere until someone's ready to receive them, and you end up with problems of unbounded buffers where you kill all these async things and nobody's ready to catch the data, and you run yourself out of memory. And you don't understand why, because all the memory is off in some async lambda somewhere that you can't see. So blocking the sender mitigates that problem. But you don't want to block the real operating system thread because you can't have that many of them and the performance is not that good. You want to block the lightweight thread. So in Go, that's fine. They've got their whole own virtual machine to do that. They also have select, and a bunch of other stuff, which are the more advanced scenarios. If you've got multiple channels that you want to read from, select will let you read from them. If you've ever done any Unix programming, any old greybeards here, you might be familiar with select on files or sockets or something like that. It's kind of similar. Now, the motto of Go is do not communicate by sharing memory. Instead, share memory by communicating. So that's a bit of a brain teaser. But what it kind of means is you've got all these things running in parallel. Don't think about how can I protect this memory with locks and things. Instead, think about how can I pass messages around the place. So how are we going to do this in C#? Well, our go-to thing at the moment for C# is tasks and async await. So we could have a task called multiply. We'd use task.run to run that in parallel. And we want to block and wait until it's finished, but we don't want to block the operating system thread. Well, hey, async await, that's perfect. That's what it does. So we'd have our await method, and then we'd print the result. It's functionally equivalent to that Go program. And if that's the complexity of the problem you have, that's all you need. Where it gets more interesting is if you have, say, two channels. So my Go program wants to send A times B, and then it wants to wait until someone picks that up. Then it wants to send an OK. How do you do that in C#? Well, you could have a tuple of tasks, and you could return the first one, and I went to try and go down the avenue of writing that code, and I got all confused, and no. What you'd like to do is have a class called channel, and you'd like to do a send and receive, and you'd like those sends and receives to block for safety, but you'd like to not block the operating system thread, so you'd like to use async and await. So proof of concept, can we do it? Yes, we can. And I'm not going to show you that example running, because it's fairly trivial. What I'm going to show you instead is a demo app that I wrote. Now this particular app, you select a folder. I'm going to select my debug folder. And what it does is it scans the folder and calculates the SHA-1 hash of all of the files. And it puts it in the UI. You can select another folder. And it also, just so that I can have a cool looking demo, build a tree map over the side here. Now, the way that this is typically done is, so we've got to go and process a whole bunch of files. And we could use an async await on each individual file. Or the way that I've often seen this done is you call the method to go and process a directory. And inside that there somewhere, there's a dispatch lambda onto the UI thread. You might have a bunch in the middle and a bunch in the end. That's a really common pattern that I've seen. And so it's kind of not nice, really, to have your file processing code have like UI dispatch lambdas in the middle of it. But it is pretty common. So what the channels that you do is sort of decouple that. So I've got my app. It's got a directory change channel. So whenever I click on that main button to change the directory, all it does is send the directory name down the channel. And then I've just got a loop while receive. Then we go and open the folder. We've got some exception handling. Then what we need to do is we need to scan the directory. And if I pick one with a large, if I pick a different folder, let's pick this one. You see we've got a large folder that's taking a while to scan. We want to have a progress indicator. So we want two notifications. We want a I'm starting and I'm finishing. And we want to achieve that for all of our sort of things. So again, rather than starting, finishing, lambdas and stuff all over the place, we can just have two channels. We can have a add to list, all done channel. And we can say, go and scan that directory in parallel and tell me when, and basically just fire me data. And then we have a really complicated data structure called a loop. And we just loop and we say, when someone says add to list, we go and put it in our data blended collection. And then we wait for the next channel, which is the item finished. And then we put it in there, and then we redraw the tree map. So I thought that was really quite neat. They let you decouple your producer and consumer code. Now the other interesting thing as well is because they're blocking on both sides, the code in the background that's doing all the scanning is not going to race ahead and scan 1 million files and bomb your UI thread with 10 million lambdas. It's only going to proceed as fast as it needs to. In this particular case, there's no point racing ahead and scanning all the files if we can't even show them on the UI. The other interesting thing about these channels is that effectively they are a sequence. So you can do things like zip and sum and so on and so forth. So with this, I'm not saying you should go back and use my experimental channel code in your production apps. Hopefully, I've got at least one person in the room to think, that's an interesting idea. I could maybe apply that somewhere. Where they're good is if you've got asynchronous work like my file scanner, which posts multiple results. They're also really good if you have this producer-consumer and you don't want one to race ahead of each other. You can have buffered channels if you do want to allow one to go a little bit faster, so you're not just switching one to one to one. You can just put a buffer size in. If you happen to like Go, they're good as well. But mainly, they can help you separate your concerns. Also, it's interesting to note that these do not replace the task parallel library. I'm not trying to eliminate any of the good stuff that Microsoft have done. I'm trying to build on top of that, and what can we do? Maybe not for async stuff, like my first example of just multiply two numbers. You don't need a channel for that. You've only got one value, just use a task. That's what tasks are for. So we're not quite at the end of the talk. Got some honorable mentions, stuff that I didn't get in. Just quickly run through this. If you've ever written a finalizer, a method with a tilde on it, it's almost certainly wrong. Don't do that. Microsoft have got some classes called safe handles, which wrap int pointers, and they're often better. Extension methods are great. If you've ever wanted to put extension variables, if you've wanted to put variables into other people's objects, you can achieve that by this class called, you can achieve an approximation of that via a thing called conditional weak table, which Microsoft actually put in for Iron Ruby support years ago. Other languages, there's Scala, gets a lot of airtime because it has this thing of everything is immutable. They have all these immutable collections. Microsoft have kindly gone and written all those for you for C#. And if anyone's ever heard of the reactive extensions are another sort of asynchronous thing, and they're an example of this going the other way. They were built in C# by people inside Microsoft, and they have gone now into C++, JavaScript, Java, and there's also an Objective-C one as well. So it's this cross-pollination of ideas. So related sessions, task parallel library, I'm all for that. Now, anyone who likes programming, you can't miss a talk by Ivan Tellson. And obviously, Visual Studio 2015's got a lot of cool stuff. Now, please complete your session eval. What I wanted to talk about this year was Microsoft's Objective-C compiler. I think that's really awesome. Microsoft has got an Objective-C compiler and an iOS runtime on Windows Phone. But it's too early. So if you like that kind of thing, give me a good eval, and I'll be here next year to talk to you about that. I wanted to leave you with this for the rest of Ignite. Expose yourself to great ideas from as many sort of sources as you can, and try and bring those back into what you're doing. Thank you.